Good morning. So excited. Last lecture of the year. We made it. We started in September, this same group, and really gotten to know each other well. It's been great. It's been fun. We're going to finish up with sort of stepping away from nuclear. We're going to talk a little bit about electrical storage because I think a lot of the new technologies like solar and wind are held back because of this. So electrical storage, methods of storing electricity or storing energy in general are where it's at in terms of the research. So let's dive in. And so what we want is storage that has a low impedance. So when something's an impediment, it's a hindrance. And so we want to be able to store energy quickly, so at high wattage, and then we want to be able to recover it quickly. Now that's sort of one of the ranking things. How fast can we get electricity out of this technology, and how fast can we put it in? We're going to talk about photovoltaics today, and then look at long-term and short-term storage. Again, I'm going to post these notes after class, so you don't have to get a hand cramp by trying to write everything down. And then we don't want our storage mechanisms to be lossy, okay? And that was the term that I had heard growing, and I thought, it's always a good idea to check the Urban Dictionary before you start using words that you don't necessarily recall. So I was like, so I'm not talking about the one who smokes pot. I'm talking about some way of storing or transferring energy where you don't lose the joules. Okay, so if you store it in a battery, there's some discharge, there's some small loss of electricity because we live in an oxidating environment. And so we have, oxidative products on the outside of that battery. There's a little bit of leakage current inside the battery, and we want to keep those as small as possible so we don't lose joules. This is the same efficiency chart we've been using this part of the course, but I've added one thing here that's new, and this is going from mechanical to a storage medium. So you can pump water uphill, and you're essentially storing it with gravity. So you're increasing the potential energy of that water by pumping it uphill. And I thought, that sounds like a potentially good idea. Has that ever been done? Yes, there are pumped hydroelectric plants. So that's pretty interesting. And then compressed gas. You could maybe, when you've got mechanical energy and you don't need the electricity because a cold front came in and everybody turned off their air conditioners, yet the power plant's still going. It takes a while to shut that off. And so you can pump things. You can take that mechanical energy and instead of making electricity, which is not needed at that point in time, pump water uphill or pump air into a vessel. So you can store that potential energy in terms of the compressed gas, and then later use that compressed gas to drive a turbine and get back to electrical when you need it. So these are some other options. So potential energy or just pressure or gravity is another storage medium. Again, we're trying to, we're really focusing on electricity, and so let's look at these different areas where we can get rid of the waste in terms of the electrical grid. And one of the largest places for waste in the electrical grid is when you have this base electrical generation that can't be turned on and off very quickly. Notice this is a typical hourly usage profile, so from midnight to midnight. So overnight, people do finally fall asleep and turn their phones off, and so there's a dip, and that was a joke. There's a dip in electrical usage, okay? And then when they wake up and start turning on hair dryers and things, or air conditioning in buildings and so on, you see this enormous peak of electrical demand. And so if we could level this out, then we could improve the efficiency of our electrical grid. It's very difficult to turn nuclear on and off like that. It's also very difficult to fire up the coal and then cool it down. What you have once you have that coal furnace burning is you've got to be doing something with that energy or just throwing it away. And so either you're clutched into the generator and making electricity, or you release the clutch and you're just burning and spinning the turbine, but you're not clutched into the generator. So you don't want to do that. You're wasting fuel. Now the natural gas turbine engine, it's a jet engine just like on an airplane, but that's clutched into a generator, and you can turn those engines on and off fairly quickly compared to coal and nuclear. And so this natural gas turbine engine has really been revolutionary. This is the past 10 to 20 years we've started using these, and that's what's at Roans Prairie. So when you're going to Bryan College Station and you pass the Roans Prairie power plant, Sometimes you'll see steam coming out of the chilling towers, and sometimes you don't. It's because it's just a load leveling power plant. And so whenever there's a heat wave coming through, that plant kicks in so that it can ramp up to level out demand. And then whenever there's a low demand of electricity, they shut the plant down. And they just turn off the natural gas, and so you save your chemical fuel for when you need it. So let's look at these leveling technologies. Same kind of thing would happen as well for wind and solar. So when the sun is shining, you need to make electricity, you probably want to store that in some way so that you can use it at nighttime. So what's the average power of a home? We've looked at our Entergy typical customer usage, and they said about 1,000 kilowatt hours. And so that's on terms of a daily basis. We're talking about 1,000 or 1,300 or so watts. You can figure out what the amperage are. I just put all these calculations in here so that you can see how they're done. And then look at this too here, that's DOE typical power rating. So 3,000 watts per home. That would be a typical power rating. If you look at your breaker box at your house, when you get a house, you'll see it's about a 200 amp breaker box. That's what we have on our house. And so this is going to be how much we draw off the grid, about 3,000 watts. Now, is there a minimum power? We don't ever really shut everything off because we have refrigerators and freezers and so on, air conditioning or heating. And so what you can do is you can turn off all your lights and go look at your meter. Then you can turn off all your computers or unplug things and look at your meter, and you can see what your minimum power rating is. You could even see if you, if you can turn everything off or pull all the plugs except for one device and see what it's pulling on the meter. This would be, I've never done this, I'm not that insane, but if you wanted to, you could analyze everything in your house from the grid level and see what kind of power it pulls. So let's look at energy storage, because this is the main question. How do we store power that's generated by wind or solar? Or if we have a building, like a huge business building downtown, and the electrical company offers us a different rate at night versus daytime. That's fantastic. We might be able to save millions of dollars by pulling off the grid at a high rate at night and then leveling that out during the day. So when our buildings boots up in the morning, we don't have this enormous draw on the grid at the high energy prices. Yes?
So is that why stuff like North Texas, THU Energy has like the free nights or free summers?
Yes, yes.
Okay.
And so it's kind of sad, but if you could store that energy at night and use it during the day, you'd have free energy at your house. Yeah. So you would need to invest, and this is where the cost comes in. We're going to talk a lot about cost today. If you could invest in some flywheel storage or lead acid battery storage that was, cost effective, and you charge that up at night off the grid free and use that during the day, then you're not paying any in electricity. Yeah.
You think they would catch on to that?
No, they want that. That's actually what they want, because they essentially, to keep their coal-fired power plant going overnight, if you're helping them level out their demand and you're not asking for electricity during the day, you allow that power plant to service more customers at the same power rating. And so they are looking at the money in the future they're going to have to spend on a new power plant versus the money they spend now. And so they would be spending more on fuel now, but they would be servicing more customers and making their plant last longer, because the enormous investment in making, paying for a new plant is off the scale compared to getting more efficiency in their plant right now. They'll even pay, Entergy will give you an enormous break if you let them come and do an energy audit on your home. And again, this may not be too relevant for you right now as an apartment dweller, but in the future, like right now in Huntsville, you can have Entergy come and do an energy audit in your home. And they'll say, wow, your water heater is really inefficient and your air conditioner is inefficient and you're spending X amount on energy when you really only need to spend Y. And if you'll make these changes and invest in these more efficient appliances, we'll give you, say half of that cost back. Like they'll pay you money to make your house more efficient, because that makes their power plant last longer in terms of servicing more customers. As people move to the area, they don't want to have to build a new power plant. So if they could get more people on the same plant, then it's worth a lot of money to them. Yeah, so it's just kind of strange that the power company would pay you to make your house more efficient, but it goes back to this right here. You know, if your house is more efficient, then this peak drops, and then their power plant can service more customers. So let's look at the different levels of energy storage. There's some plots in here that are interesting. Down here on the bottom, we've got power requirements for utility applications. So if you think about a power plant, the ones at Roans Prairie are, you know, megawatts, hundreds of megawatts of power. And so that's like power plant level. And then down here in kilowatt range, that's like household level. And then we've got different systems that we can use. So we've dealt with static batteries, like we've got our AAA batteries. You know, these are tiny. The milliamp hour ratings is essentially telling you how many joules are in this battery. And so you compare the capacities. People have gotten pretty familiar with the MAH rating, the milliamp hour rating, because of our power cells to recharge our phones. You know, used to, it's really exciting. Ooh, I've got a 500, you know, milliamp hour battery. Now I've got a 5,000, you know, and I was at Home Depot and they were, you know, on sale for $9.99, 5,000 milliamp hour battery that would charge at 2 amps. This is great. And then I went up and it was even dropped in price from the sign on the kiosk to it was $8. And I was like, okay. I went back and I got 4 more for stocking stuffers for Christmas, you know, and everybody in the family was super happy. Like, wow, this is great. So they're really helpful on band trips, you know, you've got the chaperoning in the bus and you want to, I don't know, do Instagram or something. So, but batteries, they're static, right? The reactants are in there. There's a certain milliamp hour rating. And one thing I wanted to cover in this comparison of different electrical storage media is flow batteries or fuel cells. Mm-hmm. So you've heard of fuel cells. Most of the commonly heard of fuel cells are the hydrogen-oxygen fuel cells, but there are a lot of different fuel cells. In fact, you could probably turn just about any redox reaction into a flow battery. A flow battery and a fuel cell are the same thing. Now, some of these, you know, there's strengths and weaknesses associated with all of them, but these are some commercially available fuel cell batteries for storing electricity. For storage, you run the system backwards, essentially. You're putting in electricity and you're shifting the reactants. And then for discharge, you let the reactants, the redox reaction, go in a spontaneous direction and you get electricity out. So in this flow battery, you can charge it and discharge it back and forth. You're just running electricity into the battery and running it in the opposite direction of its spontaneous direction, and you're running it uphill chemically. And then to discharge, you let it run downhill spontaneously. So this one is a polysulfide bromide fuel cell. So over here we have sodium sulfide, and here we have sodium bromide, and the sodium ions go through the membrane. And that's the current limiting step. And these cation permeable membranes are always the problem with these various systems. But they've got some engineering concepts prepared for megawatt hour, 120 megawatt hour facilities. Again, this is quite a large facility. That's power plant level in terms of its capacity. You can have some with vanadium, so vanadium 4 to vanadium 5. You've got some with zinc bromide. Now this one has been militarized, if you will. That's a shipping container, and it's got several of them in here. It can deliver 200 kilowatts and in a 2.5 hour flow battery, so it can deliver power. They can drop this down out of a helicopter and power a little small forward operating base. Pretty slick. Nice thing about it is it's 75% efficient, so you charge it up and you get 75% of those joules back. So that's pretty awesome. This one, also the lead acid battery, we use that in our automobiles everywhere. Okay. And here's a power facility that's a 10 megawatt power facility. So this huge warehouse is full of lead acid batteries. Yeah. So again, if the wind's blowing, you charge those things up, then it gets still. You would have lost those joules if you weren't using them as they were generated. So how can you store those joules of electricity? You store it in a lead acid battery. Here, this whole facility, those are all just racks of lead acid batteries. This one is, I call the fire and brimstone battery, because sodium is combustible in air. It's reactive with water and air, and this has molten sodium in it. And again, it's a sodium permeable membrane, and then it's got sulfur on the outside. And so this is a redox reaction. And if that sodium catches fire, then you're going to catch the sulfur on fire, and that's brimstone. So it's a fire and brimstone battery. And it's here's one in Japan that's installed with a wind farm. So the largest one is in northern Japan, a 245 megawatt hour facility. Can generate 34 megawatts of power. So not quite as large as Roan's Prairie. About a third of Roan's Prairie's generating capacity. Then we have the lithium-ion batteries. These are fantastic. They're about 80% charge-discharge, and you can get about 3,000 cycles out of them. They're super efficient in terms of their storage. What you put in, you can get out. But again, it's over the lifetime of these 3,000 cycles, it drops down a bit to 80%. And then we have metal air batteries. These are the button cells that you use. They're the most portable electrical batteries, because you're only carrying one of the electrolytes around. One of the reactants around. Oxygen is the other reactant. And so it has a little permeable gasket in there, and oxygen moves in and creates the other half of the reaction. And then in terms of amount of power that you can get out, supercapacitors give you the highest current. So these are not technically batteries. There's no redox reaction going on. Okay, so they're not flow cells either. There's no redox chemistry. You're just charging up 2 plates. The simplest capacitor is 2 plates. Charge those up. The repulsion of those ions drives the potential, and so then you can run that current through. And then this one, we have gravity and potential energy storage, which is what I was describing earlier, reverse hydroelectric. Water is pumped uphill into a reservoir during non-peak power periods, so at nighttime, and then they let it flow back downhill through a hydroelectric plant in order to generate power during peak demand. The same thing with compressed energy storage. So here's a compressed air energy storage setup. So the power plant's running at constant rate, nuclear plant, coal plant, so they keep it going at its most efficient rate. So it's generating electricity all of the time. And then it's nighttime, so you don't need very much. There's a drop in demand. And so that electricity is drawn off the grid and pumping air down into an empty rock formation. So these are rock formations that might have had pockets of gas, like natural gas, and say the natural gas has dropped off in terms of its pressure. And so you can pump air down into those reservoirs. We have also caverns that were salt domes that have emptied out. And so these are pretty stable places to store gas. And so you can pump air down in there and pressurize this cavern so it'll hold a lot of air. And then when peak demand comes back, you can run that air through the turbine and generate electricity with it. Now, you still take a hit in terms of the turbine's efficiency. They're about 46% efficient. So whatever you pump down there, you're only going to get 46% of those joules back when you run it through the turbine. But still, you're able to run your coal and your nuclear power plants at top efficiency. And so there's some gains there. So you run those at high efficiency, and then you lose some with the turbine, but still, it's another way to store potential energy to make electricity. Here's the pumped hydro. So this is pretty great. Here's a dam, and then look at the water drop in order to generate the electricity here. Pretty small compared to this drop. And so whenever nighttime comes and demand drops, then they'll use this flow to pump some of that water uphill. So it's really kind of strange if you think about it. You're taking, say, a drop unit of 1, and you're pumping water up a hill 5 times further. And so maybe it takes 5 units of water to pump 1 unit of water up that high. Okay, but still you're using this drop to store that energy. And so then you take this reservoir and run it through your turbines to generate electricity when demand goes up. Now this one is definitely lossy, okay, because you have evaporation.
Yeah.
Okay, so you'd want to cover that if you could, but it's a big place, so it's hard to cover something that large. But also it's gamey, if that's a word, if it rains. Okay, so if this is in a moist area, that's fantastic, because then you're going to get some free energy by getting that to trap water when it rains.
So basically, they need Jerry World just installed on top.
Yeah, that's right. Fill that stadium full of water. And then, this would work great in Oregon, places that get lots of rain. Wouldn't work so well in Arizona. You pump that water uphill, and you go up there, and there's no water. I thought I put some water up here. Where did it go? Yeah. Now, for your household and for businesses, this is a way to store energy on a smaller scale, and this would be flywheel storage. So these power units, they're little metal canisters. They look like little gas cylinders, about the size of that trash can, maybe 2 times wider. And inside is this really heavy polymer cylinder that spins. So at nighttime, when energy is free, okay, you take some of those and you run them into this deal, and there's an electric motor in there, and you spin that up, and you're storing in kinetic energy. And so these things spin up to a maximum speed, and it's like a battery. It's full. It's fully charged. And then in the morning, when your air conditioner kicks on or your hairdryer goes, then you pull on your uninterruptible power supply, and you pull those joules back off. And these are incredibly efficient. So if you need more, this is 6 kilowatt hour unit. If you need more, then you just buy more units. And so this, I think, we're going to start to see more and more, where we start to level demand at the buildings where it's used. Now, this is going to have quite a bit of inertia. So when that thing is spun up, you will have a hard time moving it or tilting it because of the angular momentum that it has. And so I think, I haven't seen this written anywhere, but just thinking about the physics associated with these, that they would need to be mounted in such a way that if there was an earthquake or whatever, it didn't, like wreck the place. Because these are going to be very resistant to motion when they're fully charged.
So when they're fully charged, they're just spinning constantly.
They're spinning inside until you use it. So you have them on magnetic bearings so that there's no friction.
Okay, I would worry about it to wear down if it's constantly.
Yeah, and so you can set these things in magnetic bearings,
okay,
so that they're not actually touching. So you have magnets here with, say north pointing towards each other and south, set up to where they're not touching. That there's magnetic repulsion keeping them apart.
It's all hovering.
Yeah, essentially hovering, yeah. Have you ever done that with the pencil and the ring bearings? You could set those onto each other, and again, there's very little friction between those. You could spin one relative to the other.
Yeah.
And you can make these magnets angled so that they look like pressure bearings, but these are repulsive surfaces, and so that they don't really touch. This does have to be fairly heavy because you need inertia. And so it needs to take a fair amount of energy to get it to spin up to velocity, and then it's going to take a fair amount of energy to slow it down. And so when you clutch into this with a generator, then you're slowing it down. And you're taking those kinetic energy joules, the mechanical energy, and turning it into electricity.
So how are those? Like, is it going to sound like you have a jet turbine in your backyard? Or?
No, these are all enclosed. It's just, if there's no friction and vibration, then you wouldn't hear anything. Yeah. I don't know that. Yeah, I don't know that. Yeah. But you can, just Google flywheel electrical storage, and you'll find companies that produce these.
So you can just keep one of these in your garage and just power your home.
Yeah, that's right. And I don't know how much, like 6 kilowatt hours we were talking about earlier. We need quite a bit more of that than that, but you can maybe use a couple of them and power your whole house. So yeah, that'd be fantastic. And not only that, it's not lead acid. You don't have any chemicals. You don't have sulfuric acid and all these buckets of sulfuric acid and lead, which is what a lead acid battery is. So there's very little chemical hazard to this. There's quite a bit of electrical hazard because you've got the high power leads. But again, getting an electrician to hook that up, everything's shielded. So these are the technologies. It's sort of a eye chart here that talks about power versus energy. The compressed air energy storage or pumped hydro, those are obviously energy. When they talk about energy applications, they're talking about power plant level. And then for power applications, that's like the capacitors, things that can give a lot of power very quickly. And so these dark circles are fully capable, reasonable, being installed right now. I mean, you have ultra capacitors, you have flywheels, lead acid battery installations, and so on, and you have pumped hydro and compressed air and so on. So we have a full range of things from high power applications where you need a lot of torque. Like they did a little drag race with one of the Tesla cars. It was just total electric motors on all four wheels, and it just totally whipped a Porsche 911 or whatever the fancy sports car was, because you had so much torque on those electrical motors from these capacitors. I mean, you can really turn those wheels. In fact, that's why we have our diesel trains. They're all hybrids. We've had hybrid vehicles since we've had diesel electric trains, because the transmission to gear down a diesel engine to just do mechanical drive on those would be so huge and so heavy that they've gone to diesel electric generators and electric motors on the trains. So whenever you see a diesel locomotive, that's a hybrid vehicle. The diesel motor is turning an electrical generator, and that electrical generator is providing an enormous amount of torque to those wheels. So it's continuously variable. There's no transmission. So it can turn those wheels as slow as it wants or as fast as it wants, as fast as the power rating will let it. So this is sort of a great chart in terms of rated power. Up here in megawatts, this is power plant level storage. So the pumped hydro is up here, compressed air storage is here. So those are power plant level. And then down here, this EDLC, what is that one? That's the capacitors, ultra capacitors. Over here is the discharge time. And so those capacitors can discharge faster than anything else. And so that will provide for an electric motor the highest amount of torque. And that's why it's very bad to stop a ceiling fan or to have electricity being supplied to an electric motor and not have that motor turn, because it's trying to turn the motor. So it's putting an enormous amount of current through the coils, and current generates heat. So if you have a motor that's trying to turn, but it's not turning, that's when you have the highest amount of current. And these capacitors can provide the most current. So they can provide the most force on an electric motor. So for starts, for an electric vehicle, you'd want to have some ultracapacitors in there so that you would have a lot of torque to get the vehicle going. And then once the vehicle's going, then the regular battery can be discharging. And then if the battery's depleted, then you need enough of a motor in there so that its electrical generator can keep the vehicle going at speed.
So the capacitor, like you said, it doesn't really store energy, but so does it stores energy and immediately just shoots it out in more of a compact?
Yes, because there's no chemical reaction going on, so you don't have to have the chemical reactants in contact with each other.
Yeah.
It's just pumping positive and negative charges. Actually, what it's doing is it's pulling them apart, and they're attracted to each other. So essentially, you have plates really close together with the same charges on them. They're really repulsive, and so you're stuffing charge in here, and it wants to get back out to reestablish zero charge, if you will.
Okay.
Yeah.
Okay.
I didn't explain that very well. I should draw it out. Then you have all of the different batteries in the middle. Lithium ion is here. Notice it's doesn't have a huge power rating. Okay, and it's moderately slow. In terms of discharge. And then lead acid here. The reason we still have lead acid batteries is this: we can store quite a bit of power in a lead acid battery, and it has a good range of discharge times. It can discharge faster than a lithium ion battery. And it also can discharge slowly. So it's got this huge range, and why would we use something so nasty and hazardous as all this lead? We have lead in all of our vehicles, this lead acid battery. It's because it works. And until we find something better, lighter, smaller, then we're going to continue to use the lead acid battery. Just like our mercury tube lights. We still use mercury tube lights because the mercury gives red, green, and blue photons. And that makes white light. And until we can find something cheaper and better in terms of the lighting, we're going to continue to use the mercury. But we're starting to see LEDs come on. And so LED lighting is going to replace our fragile glass tube lights. And I was just in a local shop here, body shop, Amaya's, and I walked into their main area, and it looked like tube lights along the ceiling, but they were just LED arrays. And it was fantastic. The lighting was great in there. I was like, this is so cool. So, this volume energy density versus weight energy density. So this would be lighter up on this axis and smaller on this axis. And so the metal air batteries, the little hearing aid batteries or watch batteries, those are the lightest and the smallest. Okay. Lithium ion is close to that. That's why we have lithium ion batteries in our phones and not lead acid batteries in our phones. Okay. They're light and small. They don't have a lot of power rating, but they have enough. We can get a full day out of a good phone battery if you turn off some of your apps. Okay. And then down here, the smallest, that's sort of in terms of volume energy density and weight energy density, the capacitors are not the best. Okay. In other words, you can only store so much in the capacitors, and so they don't have a huge kilowatts per cubic meter. But boy, they can sure deliver that in a small amount of time. Also, flywheels, again, that's not probably the best package in terms of cubic meters, kilowatt hours per cubic meter, but they're small enough that they're practical. Okay. Let's go now to power plant sized storage or generation. So here's a solar steam station in Kramer Junction, California. So these are parabolic reflectors with little quartz or glass tubes running through that have water in them. And so this is just a parabolic mirror and a tube at the focal point with water in it. And it's heating up that water and eventually boiling it and making super hot steam. And then we're taking that steam and turning a turbine and making electricity. So pretty interesting. And so then look how huge it is. And so I kind of looked at this road. This is like a regular dirt road for a vehicle. And then for scale, here's a similar road. So these have about the same size traces on these images in terms of the road. So this would be the footprint for a coal-fired power plant. And this is the footprint for the steam power plant. So you can really see the difference in terms of footprint. Okay, this 354 megawatts of capacity for the solar steam station, and this is the Fayette County where my wife's family is from, and they have 3 coal-fired power plants, and the smallest one is 445 megawatts, and that's right there. And then the 2 598 megawatt power stations. Now, that's not exactly fair to compare the footprint of the power station to the footprint of this solar steam station because I'm not showing you the footprint of where they get the coal. Okay, so this has a huge footprint up in Powder Basin, Wyoming. So if you go to Powder Basin, Wyoming, you'll see an enormous cavern where they dug the coal out of the ground. They put it on train cars and drive it down to Fayette County. So if you're ever on a Texas Railroad, you see coming by FPPX, that's Fayette Power Project Transport. So it's coal coming from Wyoming to Fayette County, Texas, which is LaGrange. And that's traveling a long way to get to this power station. Now you might wonder, isn't there coal near like Lake Limestone or Normandy? Really close by, maybe 2 hours away, Rockport. But that coal has a lot of sulfur in it. And so they would rather go up to Wyoming and get low sulfur coal versus the sulfur coal that's here in Texas. Let's go to photovoltaics. So photovoltaics, light comes in and causes a separation of charge. So a photoelectron is advanced to this conductive layer, and now it has to go all the way through your home to get back to the other side. And so that's where the trick is for efficiency in photovoltaics. You've got to get this charge separation. So how many photons in versus how many electrons you produce. That's the efficiency. So the solar irradiation is a huge amount of joules, but only 15% of those joules end up in terms of electrical potential. So you have to have charge separation. And so finding out these materials that cause this charge separation with this photoelectric effect, that's the research into photovoltaics. Then you can install these both on your house or even power level installations where you have whole power plants. And here's one in Germany. So that's a solar power plant, and it's enormous. So quite a few acres. Again, comparing that to that Fayette County Power Station. Fayette County Power Station would probably fit in one of these little sections. Okay. Now you have the cooling lake also, but you have the lake with or without the power plant. So and then you have the Powder River. So Powder River is probably the size of this. So we take the coal in an area where there's low cost per acre. So out in the wilderness in Wyoming, we destroy a lot of the surface area and pull the coal out, and then afterwards we replant topsoil and trees and grasses and carry that coal to the power plant. Whereas solar installations typically need to be fairly close to where they're going to be used because of electrical losses. So the cost of land to put in a solar plant would be cost prohibitive in a lot of places. Yes.
So on the prior slide, what does it mean by like doped with whatever?
Oh.
Because like doped with arsenic seems like good.
Yeah, so you can take silicon, and silicon's a semiconductor. So if you excite electrons into the conductive band, then it's conductive. And what you're doing is when you dope it, if you look at silicon, if you have gallium and arsenic, notice they're on to the left and to the right of silicon. And one of those is electron deficient compared to silicon, so the gallium is, and the arsenic is electron rich compared to silicon. But yet they're fairly similar in size. So you can dope silicon with both of those elements and change the electrical properties. Either give it holes by putting gallium in there. So compared to the silicon, there's like a missing electron on the gallium. Or compared to the silicon, there's an extra electron on the arsenic.
So basically, you just have like a big piece of impure silicon.
Yes, and so you're adjusting the impurities to change the electrical properties. So think about the HOMO-LUMO gap in MO theory. We had a HOMO-LUMO gap. We had electrons in the HOMO and holes in the LUMO, and there was a gap there. Adding in these dopant molecules can adjust that gap. And you want to make it small enough or tune it to where light from the sun can cause electrons to pop up and become conductive. So it's just the material science of trying to figure out these efficiencies for creating electron hole pairs that have to go through the circuit in order to reestablish electrical neutrality.
Okay.
Yeah.
And then silicon would be used just based on its abundance.
Yes, and also it's just in a great place right there under carbon because you have lots of options for the gallium and the arsenic or indium and antimony. You can dope it with these different elements and tune its electrical characteristics. And then we have enormous experience dealing with silicon because of our semiconductor industry. So we have a great capacity for being able to deal with silicon, and it's super abundant. Yes.
Do these solar panels have like a lifetime?
Yes, everything does, and so that would be part of your analysis. What's the lifetime cost of these different things? And here's a great place to go if you're interested in solar. It's the National Renewable Energy Laboratory. It's part of our government, and they have a solar calculator. You type in your longitude and latitude and so on. You type in your zip code, and they'll do all that for you. They'll tell you how much sun is hitting your property on an average day, an average year, and they'll say what size house do you have and all of that, and then we'll tell you how much money you could generate, like $470 of electricity per year if you installed solar for your home at 3,000 watts. And so it's pretty slick. And they have some rules of thumb, and I have these for the calculations in the practice test. Any of the ones that deal with converting from like a 3,000 watt home over to the cost, or from 3,000 watt home over to the size of the panels that you have to put up. And this is, again, these were numbers from 2008. So I looked this morning on the National Renewable Energy Laboratory to see, because I know the costs have come down. I wasn't too really excited about this because 3,000 watts per home, that's $24,000 to install all of this. And that's a chunk. I mean, it's going to take a while. And if the life cycle cost, if this is great, you say, well, I could pay for it $400 a year. It's going to take a while to get that money back. And if the panels degrade in that time, I'll never get it back because maintenance costs, replacement costs, broken panels, bird poop on the panels, cleaning, all of this stuff that you have to deal with. You probably would never recover that cost. But now the prices have really dropped. This was $8. That's up here at the top. It's $7 in 2010. Now we're at $2.70. And so at $2.70 per watt, now it's $8,100 per home. Not bad. We're getting really close. And so I'm really excited about this. Now down here in terms of the efficiency and square footage, right? How many panels you need to put? Because ideally you'd want it to be just on the south side of a roof. Whatever roof is facing south where the sun's hitting your house. If you have to cover all the square footage of your home, it's not going to work on the north side of a sloped roof. So you really need to get the energy rating per square foot to where you could just put panels on the south side of your roof and hopefully not the whole surface, just an easy portion to get to. And so I've seen some crazy claims of 15 to 18 watts per square foot, and none of these were at the NREL. These were like solar companies selling you things, and I'm like, I don't know. So I don't know what the new number is in terms of efficiency. So this one, that's why I put crazy claims. I didn't adjust this number. But if it were 15, now we're talking about 200 square feet. And if it were 18, we're talking closer to 150 square feet. So that would be fantastic because that's not much area. So if you could power your home on a sunny day with 150 square feet, go ahead and make it 200 and get yourself a energy storage medium. So you store that up during the day and you can run your AC at night and it'll be in good shape. This is a crazy one, radiothermal batteries. We're going to hit a few weird ones lately. These are how our satellites are powered. Okay, when they get far enough away from the sun, the solar power is not great because there's not a lot of photons hitting those panels. And so they have inside this enormously hot radioactivity, like one of the cesium or maybe even the strontium or cobalt-60. And it's generating an enormously hot surface, and they're using the thermocouple conversion, straight from heat to electricity. Not very efficient, but it's never going to run out. The lifetime of the electrical components is shorter than the lifetime of the radiothermal battery. So, and then here's one that we've not ever been able to capture. Yeah, lightning. So, the point is it's a little crazy to think about, but there's electricity everywhere. Every electrical storm comes through and, gives you, 300 kilowatts. That's a lot. Okay, if there was some way to capture that. We have this battery, essentially. The fair sky resistance, 200 ohms, 1 amp, ground, the ionosphere. We have an enormous battery called our atmosphere, and we're not utilizing it. So once again, whenever you hear somebody say, at current technology, that's just invalid. It's a nice thing to do in terms of extrapolation, but from the very beginning, at current technology, that phrase is way too conservative in terms of estimating things, because we're always innovating. And you guys are the ones that are going to be doing the innovation, or at least teaching others about it. So here's a lightning strike, 200 amps, 600 megawatts, but the time is 1 millisecond. So that was, 1.7 kilowatt hours per strike. And this was a video, and that's lightning striking a plane. So it's going through a plane and going to the ground. I just thought that was a cool video. And this plane just flies right along. You know, they got everything shielded, and it just goes around the outside of the plane. It's probably pretty loud to the people on the inside, but, you know.
So basically that came on like Back to the Future that was like something.
Gigawatts, yeah. It wasn't quite gigawatts, no. Well, it's 6 gigawatts, right? Megawatts, yeah. So that's pretty crazy. So yeah, Back to the Future. So next time we'll do a review and talk about the practice test and the final and so on. So it's been a great semester. You guys really have been an enjoyable class. And this whole year, as people have been asking, how's class going? I say, it's really great. I've got a good group of students this year, so you guys can feel proud.